Welcome back to Astronomy. In Chapter 15, we're looking at a survey of the stars. And this video is part 2. We're going to look at stellar temperatures. As you look at this picture of a cluster of stars, you see various colors. You see the blues and the oranges and whites. And these colors are indicative of their surface temperatures. When we refer to the temperature of a star, we will mean its surface temperature. In chapter 14, when you studied the sun, you learned that the core temperature was very, very hot, hot enough for nuclear fusion. And then as you move from the core outward to the surface, the temperature got cooler and cooler. And then once you got to the photosphere, into the chromosphere and the corona, the temperature actually increased. But in the context of when we're comparing stars, when we talk about the temperature, we'll be talking about the photosphere, meaning the surface temperature. Do you remember the surface temperature of our sun? 15 million Kelvin, 10,000 Kelvin, or 5,800 Kelvin? 5,800 Kelvin. That's going to be important in this chapter and in this unit on stars because it's one of the main variables that we use to compare stars, the surface temperature. So you should know that the sun is 5,800 Kelvin. And again, in Fahrenheit, that's something like about 9,900 degrees Fahrenheit. Surface temperature determines the color a star emits. You learned this back in chapter 5 when you were learning about thermal radiation. And in order of temperature, it's what I call a modified Roy G. Biv, modified colors of the rainbow. So red is the coolest, and then orange stars, and then yellow stars. And there are no green stars. But rather, if a star is hotter than a yellow star, it's a nice mix of all the different frequencies, and they just blend together, and it looks like a white star. Hotter than that is a blue star. So these are the 5 colors that stars are: red, orange, yellow, white, and blue. The hottest stars, the blue ones, tend to be about 50,000 Kelvin. The coolest stars about 3,000 Kelvin. And keep in mind again, the sun is about 5,800 Kelvin, so towards the cool end of that. Astronomers can discern the surface temperature of a star by analyzing its emission spectrum. Remember back to chapter 5, you learned about how atoms behave when the electrons get hopped up to higher energy levels, then they fall down, they give off certain discrete frequencies of light, and those frequencies depend on what element it is. So, as you learned in chapter 5, the emission spectrum tells us what elements are there, not just what elements, but if they are ionized atoms, whether they are singly ionized or doubly ionized, whether they are molecules. The emission spectrum tells us that. Stars of different temperatures will have different atoms or ions on their surfaces. You also saw this back in chapter 5. This chart going from increasing temperature, think about how matter behaves at very low temperature, it's solid, and then liquid and gas, so it's generally going to be in the molecular phase. But then you get up into thousands of Kelvin, and there's molecular dissociation where the molecules break apart into their individual atoms. And so when you get up to too high of a temperature, such as inside a star or on the surface of very hot stars, you're not going to see any molecules. And if you do see molecules, you know that it's a relatively cool star. We crank up the temperature even more to tens of thousands of Kelvin, and then we have the plasma phase where electrons start to get stripped away from the atoms. The more ionization there is, the hotter the temperature. And then we get up into millions of Kelvin, like deep inside the sun, and it's fully ionized plasma. The level of ionization reveals a star's temperature. Molecules only exist in the coolest stars because at higher temperatures, molecules don't exist. And highly ionized plasma will exist on the surface of the hottest stars. Lines in a star's spectrum correspond to a spectral type that reveals its temperature. When they were first classifying stars, as is often the case in science, when a science is in its infancy, uh, they don't know exactly what they're doing, what the best pattern to look for are. And so stars were classified as A stars, then B stars, then C, D, E, so on down the alphabet. But then, as they were learning more about stars, they realized that the order of the categories needed to be shuffled around, and it was best to go by spectral type. And they shuffled around the order, but never rearranged the letters. And so the letters are in this shuffled order. So there are O stars, and we're talking about the spectral type, then B stars, then A, then F, then G, then K, then M. So that goes from the hottest to the coolest stars. We're not going to get into the details of what exactly defines an O star or a B star, etc., but it has to do with what spectral lines are found in those different types. You can see here with M, the coolest type of stars, we can see titanium oxide right there. That's a molecule which is only going to exist at cooler temperatures. What you should know is that stars are classified by spectral type from hottest to coolest in this order, O, B, A, F, G, K, M. Here are the letters of the spectral types from hot to cool that I expect you to remember, O, B, A, F, G, K, M. These correspond very roughly to the colors from hot to cool. Blue is generally the color of O and B stars. A and F stars are typically white. G stars tend to be yellow, K stars orange, and M stars red. I say typically because these colors are subjective. Different observers may perceive slight differences in color. For example, someone might look at a K star through a telescope and it looks red to him. Someone else might look at an M star and will see it as an orange star. And so these color and spectral type correspondences are rough guidelines. An astronomer at the early part of the 20th century came up with a mnemonic sentence to remember the order of the spectral types, O, B, A, F, G, K, M. O, be a fine girl, kiss me. Test yourself. Which of these stars is the hottest? So you need to remember the order of the spectral types, O, B, A, F, G, K, M. So of those listed, A stars are the hottest. Which of these lists the spectral types of stars from hottest to coolest? O, B, A, F, G, K, and M. Which of these lists the colors of stars from hottest to coolest? Remember, from coolest to hottest, it's modified Roy G. Biv. So red, orange, yellow, not green, but white, and then blue. And so from hottest to coolest, it's going to be blue, white, yellow, orange, red. All right, continuing on. The spectral types, O, B, A, F, G, K, M, are further broken down into subtypes, 0 through 9. So for example, our sun is a G star, but there are some stars that are G stars that are a little warmer than our sun. Some are a little cooler than our sun. They're all still G stars. How do we distinguish them? Well, by subtype, 0 through 9. So within any given type, there's a subtype. 0 is going to be the warmest and 9 is the coolest. And so whereas previously, a few minutes ago, you learned the spectral types in order O, B, A, F, G, K, M. Now we're going to break down those types into 10 different subtypes. So O0 would be the very hottest, and then O1, O2, O3, etc., down to the coolest O stars, which are still very hot, O9, and then we get to the B stars, B0, B1, B2, B3, etc., to B9, and then A0 through A9, etc., all the way down to the M stars, and we end with M7, M8, and the very, very coolest stars are M9 stars. Why aren't there any stars cooler than M9? Well, that's because M9 is the lowest temperature, which corresponds, as we'll get into later in this chapter, to the lowest mass and the lowest core temperature that can possibly be a star that has sustained nuclear fusion in the core. If it were a ball of hydrogen helium gas that's not quite that hot, it would be something else. At 5800 Kelvin, our sun is a type G2 star. So I want you to remember that. Previously I said it's a G star. Now we're getting more specific. It's a G2 star. So it's on the warm end of G stars. It's a bit cooler than a G1 star, which is going to be about 5900 Kelvin, and it's a bit warmer than a G3 star, which would be about 5700 Kelvin. What have we learned? How do we measure stellar luminosities? This goes back to the part 1 video. If we measure a star's apparent brightness and distance, we can compute its luminosity with the inverse square law for light. Remember, the inverse square law means that the apparent brightness is related to the square of the distance and the luminosity. Parallax tells us the distances to the nearest stars. How do we measure stellar temperatures? A star's color and spectral type both reflect its temperature. Let's do a quick review from the part 1 video, thinking about the brightnesses of stars. You learned about the luminosity of stars. You also learned about the apparent brightness, how bright it looks. Stellar luminosity refers to the power emitted by a star. The higher the number, the brighter the star. For example, let's look at these two stars here. Rigel, it's a star in the constellation Orion, is 66,000 times the sun's luminosity, 66,000 times brighter. Therefore, it is 66,000 solar luminosities. Another star, Sirius, is 25 solar luminosities. It's 25 times brighter than the sun. Both of the stars are much brighter than the sun, and Rigel has more than 2,000 times the luminosity of Sirius. So if you compare these numbers, Rigel is 66,000, Sirius is 25. So Rigel is much brighter than Sirius. Now let's talk about apparent magnitude. It refers to the brightness as seen from Earth. The smaller the magnitude, the brighter the star looks to us. And remember from the part 1 video, that comes from the ancient Greek Hipparchus, who set up a system where he said magnitude 1 stars are the brightest, then magnitude 2 on down to magnitude 6 are the dimmest. So the smaller the number, the brighter it looks to us. So let's go back to our comparison of the stars Rigel and Sirius. Rigel has an apparent magnitude of 0.12. It's a pretty bright star in the sky, one of the brightest. Sirius has a magnitude of negative 1.46. So given that Sirius has a lower number, a lower apparent magnitude, that means it looks brighter to us, given our distance that it is to Sirius and versus to Rigel. So Sirius magnitude is lower than Rigel's, which means that it looks brighter to us on Earth. Although, remember, Rigel, thinking about the previous screen that I showed, Rigel is actually much brighter in true luminosity than Sirius. Astronomers classify stars based on two factors: luminosity, which we discussed in the part 1 video, and temperature, which we've discussed in this video. The next part, we will bring these together, comparing luminosity of stars with temperature, and we'll look at what we learn when we compare them. Before we go, test yourself. Do you remember in order the 7 spectral types of stars? I bring this up because it will be important for understanding the rest of this chapter and this unit. We start with O being the hottest, B, A, F, G, K, and the coolest stars are M stars. Memorize that order. How are these spectral types ordered? OBAFGKM, they are ordered from hottest to coolest. That is the end of the part 2 video on stellar temperature. Have a great day.